All right, constructing models notes. This is your first set of notes for constructing models. Very similar to the last section that we did, interpreting linear models. Except for right here I kind of talk about, instead of them giving you an equation or an expression, you have to choose the correct one for a given situation. So usually they're going to ask you what equation or what expression could be used to model or to represent a certain problem. And this is something that, like coders, if you're somebody who's interested in programming, a lot of times you're given the parameters or all the different inputs that could happen at a job or in a business, and you are trying to code an app or code a software that's going to calculate things based on a bunch of different inputs. So if you're a programming type person, this might be kind of up your alley. If you're not, these questions can be kind of weird, but I'm going to try to give you some strategies of how to solve it. So let's just look at one. Example one, at a school, there are A grade levels and B students in each grade. If a school buys N stickers to be distributed equally, which of the following gives the number of stickers each student receives? Most kids are going to look at that and not see any numbers. You got three variables in the first line. You're going to bail out and just pick one. That's what I want to try to avoid you doing. I want to try to get you to kind of battle through here. So let's digest what's going on. We have A grade levels. We have B students in every grade. And then N is the number of stickers that we're going to try to distribute. Now, what we're really after, the very final question says, which of the following gives the number of stickers each student receives, or each student gets? So our final question over here is, how many stickers per student? Well, since there's no numbers in this problem, one of my biggest strategies that I like to use the most, and I know Mr. Davis and I both use this a lot, is we like to choose our own numbers. We like to put our own numbers in the problem, calculate it out, and then see which way it would work. So for instance, if I'm thinking about a high school, a lot of high schools around here have 4 grade levels. So I'm going to choose A equals 4. So that's the first number that I just picked. How many students are in each grade? I'm just going to kind of make up a number. I'm going to say, well, and maybe I want to pick numbers that are really nice. Let's keep it easy. Let's just say that there's 100 students in each grade. So I chose this number. It wasn't in the problem. I'm just choosing it. So right away, just kind of from those two pieces there, I kind of gather from both of these, if there's 4 grade levels and there's 100 students per grade, if I times those together, that means that there's 400 kids in the high school, okay? Which some schools are that small, some schools are a lot bigger, but since there are numbers, we're going to keep it small. So there's 400 kids in our school. Now, if the school's going to buy stickers to give everybody an equal amount, how many stickers would we want to buy? Well, I don't know. Maybe I want the answer to be 10 stickers per student. Maybe I want this answer to be 10 per student. So if I want there to be 10 per student, and there's 400 students, I'm going to need 4,000 stickers. That's going to be how many I'm going to have to purchase. All right. Now, you could have just chosen a number of stickers. You could have just chosen 1,000. You're going to end up with a decimal for the stickers per student. So sometimes I like to kind of control what my answer is going to be. So now let's go through and let's kind of look here and see which one of these situations could work. So maybe I'm going to try part A. And A says that A times B divided by N is going to give me my number of stickers, which I'm looking for it to be 10. I'm kind of hoping one of these answers is 10. So let's try it. If I do A, which was 4, and then B, which is 100, and if I divide that by N, which was 4,000, well, when I work that out, I get 400 divided by 4,000, which is basically 0.1. So what this one does, this tells me that I would have 0.1 stickers per student. And I know that's not right. I'm looking for 10 per student. So it can't be this one. That's no good. So I move to the next one. A times n. So 4 times my n was 4,000. And if I divide that by the number of students in each grade, which was 100, well, that would be 16,000 divided by 100. So 16,000 divided by 100, which would be 160, I believe. And that's way too big. Every kid's not getting 160 stickers each. So this can't work. If I try the next one, b times n, well, that's going to be huge. That's going to be 100 times 4,000 divided by 4. So, man, that's going to be really big. That's going to be basically 100,000. That cannot be right. Every kid's not getting 100,000 stickers. So I'm getting a little nervous here. I hope the last one works. So we go to plug this one in, and I do 4,000 divided by 4 times 100. 4,000 divided by 400 is 10. So luckily, this one worked out right. So this would be the expression that would calculate the stickers per student. Now, as you get better with these, you may not have to go through all those numbers, because you might realize that to do stickers per student, the number of stickers over the number of students, to calculate that, well, the number of stickers was just n. And your total number of students, well, to find that, we multiplied a times b by each other. And if you notice, this right here is that same expression. So you may have to put numbers in and just calculate them. You may just kind of be able to write out the units and see what letter goes there. But it kind of depends on what each person sees on their own. All right, number 2. This one's a weird problem. And again, these are weird, nasty problems that, I've never seen in my real life, but the SAT seems to think that they're a good gauge of trying to spread you guys out and determine, trying to sort kids. But it says a carpenter lays X bricks per hour. So this is my first variable. So many bricks per hour. And we're going to do that for Y hours. So a carpenter lays X bricks per hour for Y hours. Then, so at another time, they're going to lay X over 2 bricks for 2Y hours. And then in terms of X and Y, how many bricks did they lay in total? So we need the total bricks done. So, again, I'm going to pick some nice numbers. How many bricks can I lay an hour? Well, it depends on how big they are. I'm going to pretend these big bricks here at school, the big cylinder blocks. And if I got to put mortar on them and all that type of good stuff, I'm just going to say that I'm going to do 10 bricks per hour. And I'm going to say that I want to work for Y hours. So let's just make Y be 8. So I've chosen an X, I've chosen a Y. And if I want to figure out how many bricks I did during that session, well, if I did 10 bricks per hour times 8 hours, that would give me a total of, I did 80 bricks that time, that day. All right? Well, then the next time, I'm laying X divided by 2 bricks. Well, I chose X to be 10. So 10 divided by 2 bricks would be 5 bricks. So I'm doing 5 bricks. And 2 times Y hours, so that would be 2 times 8, which would be 16 hours. Well, that's also going to come out to be 80 more bricks. So notice what I'm setting up over here. I'm setting up bricks times hours to get the total. And when I add those up, 80 plus 80, it looks like I did 160 bricks total. All right, that's the grand total there. So what I'm going to do is I'm going to come over to all these equations that they give me, and I'm going to try to plug x equals 10 in and y equals 8 in. And I'm going to do that, and what I want it to come out to be, I want it to come out to be 160. So if I come in here to the very first one, and I plug in 2 times x times y, I luck out. Right there, I get 160. I think this is going to be the right answer. If I try all the other ones, like maybe I'll try the bottom one. Had a couple kids tell me that they thought the bottom one looked good just because they saw this fraction here, so they thought the answer probably had a fraction in it. A lot of kids that are going to guess would probably guess B or D. So I'm going to try D. If I did 3 divided by 2, well, that's 1.5. X is 10 that I chose. Y was 8. Well, if I try this out, 1.5 times 10, that's 15 plus 24. Well, that's only 39 bricks. That's way too short. And you're going to find when you plug it in these other numbers, none of those other ones work as well. Now, again, you may have saw when you first looked at your total, when you did bricks per hours, bricks in hours, you basically just multiplied x times y. All right? X times y. And then we added to that, when we did these two numbers, we multiplied these two, which was x over 2 times 2y. And I'm going to put over 1 just because it's easier to multiply a fraction times a fraction. And that's what would give me the total. So when you work this out, you get xy plus, well, over here, when you multiply straight across, you get 2xy over 2, which these cancel. And so I end up with just xy plus xy, which is the same thing as 2xy. So that's algebraically why A works. I don't recommend most kids try to go down that route. I would just try to go down the choose your own numbers route and get the answer that matches. That's the way that I do a lot of these questions. All right, moving on to example 3. It says, an internet service provider charges a one-time fee of $100. So we have a one-time fee of $100. Doesn't matter how many months you join, just one time, $100. And then you got to pay $50 a month. So $50 each month. So $50 per month. And it says if C, so here's where we get kind of weird. If C customers join, so C is going to represent my customers, and I'm going to need to choose a C here for this problem. And then M is going to represent months. And so I'm going to need to choose an M here. Which of the following expressions could give the total amount in dollars the provider has charged the customers? So what's going to be, again, the total amount? So if I want to program a billing feature, and I, as the owner of this company, I want to know how much I'm going to make per month, or make after a certain total of months, I need to know how many customers I have, and I need to know how many months are we charging for. So let's just make this really easy. Let's just say that we have a nice, simple amount of customers. That's, let's say we have 20 customers, a really small company. And let's say we want to do this, and I want to see how much I have after the first 3 months. All right? So let's just kind of go back to the numbers. If I have 20 customers for 3 months, well, let's try to figure out my money. How much am I going to make? Well, let's knock out the one-time fee first. I have 20 people paying me $100. So I have 20 people paying me $100. Then I got to add the monthly charges. So then I have 20 people paying me $50 a month. But then they're going to do that for 3 months. So I think if we do our total money here and we add all that up, we're going to have $2,000 plus, that's going to be 20 times 50 is 1,000 times 3 is 3,000. So 2,000 plus 3,000, it looks like I'm making $5,000 the first 3 months, which isn't that great. I'm on pace to make 20 grand for a year. I better get some more customers. But I at least have a model here that works. So what I could do now is I could grab these numbers that I chose. I chose my 20 for C, and I chose my 3 for my M, and I can go over here and I can plug in 20 for C and M for 3, and my hopes are I need to get 5,000. One of these expressions better give me $5,000. And I'll try one just to show you. Like, I'm going to try one that I know doesn't work. I'm going to try the bottom one, D, just because I have some room down here. So I'm going to do 100 times the 3 months plus 50 times 20 customers times 3 months. And if you notice, this looks a lot like this, just in a different order. But the front part's messed up. So I know this is going to come out wrong. I'm going to have 300 plus 3,000, which is only $3,300. And that's not right. I need 5,000. So I can scratch him off. And I would keep going until I got the one that's right. But if you notice over here, if you can kind of see that, you know, the things in the problem that weren't there, this is what was in the problem. I did not pick the 100, and I did not pick the 50. That was their numbers. Here's what I picked. I picked the customer, and I picked the customer, and I picked the month. And if you look at that, that looks a lot like this one, but the numbers are just reversed around a little bit. They did 100 times C, plus they put the 50 in front, and then the C, and then the M. These are the exact same expression. So as long as you're kind of mechanical on how you set up your numbers, as you do more of these, you will get better. Trust me. I don't expect you to be really good at these after just doing 3 or 4 examples. These are tough problems. But after doing A, B, C, and now you've got, 20 to 30 problems under your belt, your brain just starts to see patterns. But if you don't put in this kind of work, it's going to be very difficult to see those patterns. Last problem. We have a table here, and let's see what's going on. We have days of the week on the left. We have average speed. So our S is our speed. Over here are our calories burned, C. So it says on certain days of the week, Elaine runs for an hour on the treadmill. Every day she ran the last week, she shows the average speed in miles per hour and the calories burned. If the relationship between C and S can be modeled by a line, by a linear function, which of the following best models the relationship? So one of these formulas here works for the chart. Meaning that if you plug in these S's, all of these numbers here are S's in this column, and all of these numbers are C's. If you plug S's and C's in there, and this over here actually is C of S. It's what are the calories after you plug the speed in. Kind of think of it as a Y almost. So we got to find out which one works. Well, you could just start trying them. The problem is you're going to have to try this S and this C in all the equations and see which one it works in. And just because it works in one of the equations doesn't mean that another pair of numbers is going to work in that equation. We really need all the numbers to work in the same equation. That could be pretty time consuming. But if that's all you got, right now you'd want to start plugging stuff in and you'd want to give it a try. So for instance, let's just pick the fast day. She did 8.5 was her speed, and her calories based on speed were 720. So let's try to put these numbers in and see what happens. So I'm going to come right down here to this first one. Is it true that 30 times the speed plus 400, well, let's see what that equals. So I'm going to grab my calculator here. And I'm going to do 30 times 8.5 plus 400. I get 655. That does not jive with the chart. The chart says I was supposed to get 720. So this one cannot work. So then I'd try it again. I'd try to plug it in the next one. And I'd say, hey, 30 times 8.5 plus 210. I honestly don't even have to put that one in the calculator because I'm only adding 210 instead of 400. So that one's going to be even smaller. It's going to be 190 smaller, which is 465. Not you. I'll try another one. Maybe I'll get lucky here. I do 80 times 8.5 plus 40. See what happens there. 80 times 8.5 plus 40. 720. Man, this one is looking good. So this is a possibility. Let's try it in the last one because it might work. I can write other equations that make these numbers work. So let's try another one. 90 times 8.5. Oop, not plus. They switched it up on me. Minus 30. Well, 90 times 8.5 minus 30. 735. Close, but no cigar. So you're out. So right now I feel pretty confident the correct answer is C. Now, another way you can do this, if you view this chart as a graph, the independent variable would be speed, because whatever speed you're going determines the amount of calories. Or another way to say that is the calories depend on what speed you're running. So, this down here is the independent variable. This one depends on the other one. Well, these are really just ordered pairs. This bottom point right here really means that if I'm at 8.5, then I'm going to burn the most calories, 720. That's a dot on the graph right there. 8.5 is 720. You can kind of think about that as an x comma y. Or in this case, a s comma c, or x comma y, however you want to think about it. Well, then let's pick a smaller one. Like let's pick, when she goes slower, she burned less calories. So let's pick a 6.8, and she's doing 584. So if this is a linear model, which they say that it is, a 6.8 and a 584, you could think about this as a slope as a rate of change. Slope is how much you're changing by. So if I calculate this, so I want you to get used to thinking of slope is change. It's a rate of change. And I know some kids like to say it's rise over run, which is really how much the y is changing compared to how much the x is changing. So let's do rise over run. So how much did we go up? Well, we went from 584 to 720. So 720 minus 584. 720 minus 584. is 136. We went up 136 calories. Okay. Well, what did our speed increase by? Our speed went from 6.8 to 8.5. So the difference between those two, 6.8 to 8.5, that's 1.7. So we basically went up 136 calories by increasing our speed 1.7 miles per hour. And if we divide those out, 136 divided by 1.7, we will have a slope of 80 calories burned for every 1 mile per hour. And look right here, our slope was 80. So that's another way to analyze these problems, is you can calculate slope and you don't have to do all this plugging and chugging. But I want to give you options. Different kids see it different ways. I do problems differently all the time. But hopefully you can use these notes to kind of help you along this week through modeling A, B, and C worksheets. See you.